approximating solutions. Some equations are just too hard to solve. And approximating, and we can get good approximations if we use the right method. The first idea is a very simple idea. If you can trap a solution between 2 points, and the curve's continuous, and that's the key, curve's got to be continuous for this to work, then you can keep halving the interval until you trap that solution into smaller and smaller intervals. Now, depending on how accurate you want the answer, then how many times you halve your interval. It's all right. So, key is, got to be a continuous curve. So there's some random continuous curve. If it is continuous, and we've got two function values, so there's A, we know function A is positive, and there's B, function B is negative, then it must cut the axis somewhere in between. Can't go from positive to negative without being naught at some point. So we know there must be a solution between A and B. That's the basic idea. A quartic, not easily factorisable. So, I mean, theoretically it should be able to be factorised. Might you need complex numbers in some situations, but we're told that, well, at least we hope there is a solution between 1 and 3, otherwise this is just a nasty question. So we assume that, yes indeed, there is an answer between 1 and 3. But just to prove it, let's find function 1. Oh yes, function 1 is negative. Function 3 is positive. We certainly know it's a continuous curve, so yes, a solution does lie in between 1 and 3. So the logic says, well, let's try the middle. So that's why we halve the interval. We find the average of the two numbers. Does it work? Well, no, it doesn't. That's not the solution. However, I can now trap it between a smaller interval. You see, now I'm not going to plot these points accurately. It's more the sign I'm interested in. We now know function 1 is negative. We knew function 3 was positive, but we also now know the function 2 is positive. So therefore, I can make my interval smaller. Instead of saying between 1 and 3, it's now got to be somewhere between 1 and 2. I can halve the interval again. So 1.5, it's negative. So all right, we knew 1, 2, but 1.5, we've now trapped it somewhere in between 1.5 and 2. Now, they've said they want the final answer to 2 decimal places, so we'll keep going. 1.75, it's negative, so all right, that means I've now trapped it between 1.75 and 2. Okay, try again. 1.88. Now notice I didn't bother going 1.875, I think is the actual answer. So I only want the answer to 2 decimal places. So 1.88. Negative 2.75, all right. Okay, so we've now trapped it between 1.88 and 2. Let's do it again. 1.94. It's negative. Okay. I now know it's in between 1.94 and 2. Let's do it again. Now, this is sounding real tedious, but of course, in reality, we can use spreadsheets and things like that, and it does it very quick. 1.94, we got 1.97. Ooh. Now it's tempting to say, to 2 decimal places, that's 0, so there's my answer. Problem is, it didn't say get the answer accurate to 2 decimal places. It was the number we're putting in. We don't know what the graph looks like. It might come down really close and then shoot back up again. So it might not be close to the actual answer. Let's see. We're going in between now 1.97 and 1.94. Average those, I get 1.96. That's negative. Okay. Well, I now know I'm in between 1.96 and 1.97. So the question is, remember we're doing this 2 decimal places. Well, I don't need to halve the interval again, or do I? Because 1.96, well, if it happens to fall before 1.965, I know it would round down to 1.96. If it happens to happen Happens to happen. After 1.965, then I know it would round to 1.97. So the question I now need to know is, well, where is it closer to? 1.96, 1.97. So in fact, I do one more. But I do it to one more decimal place. 1.965 is negative. Therefore, it cuts between 1.965 and 1.997. But all of the numbers from 1.965 to 1.97 round to be 1.97. So that is going to be my approximation to 2 decimal places. Okay? So when we finally get it trapped, we just do one more to one more decimal place so we can see, okay, which half of that interval does it lie in? Which one would it round to? There's a difference between what will happen in the test and what we're doing here. This is the method. As I say, you put it into a spreadsheet, bang, it doesn't matter how many times, you can get to hundreds, it doesn't matter. Computer will do that very quickly. In a test, they're more interested in, do you know the method? So they might just say, oh look, just use halving the interval a couple of times to come up with a better approximation. Okay? Now in the textbook, they might get you to do it as well, because you've got time to... There's another method, which is, well, we call it Newton's method, but yes, someone's heard of Rapson, have they? Okay, really it's Newton-Rapson's method. Poor old Rapson. Newton must have been a bully. Okay, so Newton's method of approximation. It actually works quite nice if your first approximation is good. And that's the key to this one. Your first approximation needs to be good. What it does in the formula is basically finds where that approximation, if you were to draw a tangent at that x value, when it hits the curve, it finds where the tangent cuts the x-axis. And so if the curvature is good, that tangent should come closer to the solution. So here's a random curve. Say I took my first approximation there. I'd go, right, that's where it cuts. So x1 would become my next approximation. And then I could keep going and so on. But up there, if I had chosen the stationary point for x0, that the technical term for that is pathetic. Because, of course, it's never going to cut the x-axis. So that would be a bad choice. That would be a bad choice. So here's how we do it. Don't worry, you don't have to do this each time. We'll eventually come up with a formula. Well, okay, the slope of that tangent would be whatever function x0 is minus 0 over x0 minus 1. So slope formula. Okay. Now, if I rearrange this formula, so a little bit of manipulation there, I end up with x0 minus x1 is function x0 over f dash x1. So in other words, I now can write a formula for x1. So x1 would be x0 minus function x0 over the derivative of x0. So if my first approximation is good, I can plug it into that formula and I'll come up with the next approximation. The biggest mistake people make is putting the derivative on the top instead of on the bottom. The way you remember it fails if you're at a stationary point, because you can't have 0 on the bottom of a fraction. So the derivative's on the bottom. Now, I'm pretty sure in this modern age of resource sheets, yeah, it is on the reference sheet as well. So if you do forget, well, just look it up. Make sure you get it right. And then, of course, you can keep going and keep going. We could generalise that by just simply saying xn plus 1 is xn minus, and so on. So let's do that same question. By the way, we have to pretend we don't know our approximation. Okay? So we go, okay, well, there's the function. There's my derivative. I'm going to need those things. Now, I need a good first approximation. It's in between 1 and 3, so I'll pick 1.5. That's logical. Yeah, I know it would have been logical to pick 2, and you'll see why I didn't do that in a sec. Okay, oh yeah, I'm going to pick 1.5 for my first approximation. So there's function 1.5, there's its derivative. Sub it in, I get, 2.21. Okay. Well, let's try it again and let's see how we go. Because function 2.21, that's not 0. It's 9.2744. So we'll try again. Well, the derivative is 45.1754. Sub it in the formula, and we get 2. Now you know why I didn't start at 2, otherwise we'd be here straight away. So, okay. So, what about function 2? Oh, function 2 equals 1. Not right. So the derivative is 35. Let's sub it in, and again, now you know why I didn't start at 2, because remember, pretend we don't know, we know that that's the answer. I would have only done it once, but no, we don't know that's the answer, okay? Sub it in. Oh, that's close. That's real close. What's the derivative at that point? 32.58. Sub it in. When look at this fraction, 0.001. It's virtually 0. And so we come up with the same number. Well, with this method, when I come up with the same number, well, I'm going to stop. I mean, that's obviously the answer, because it doesn't matter what I do now. I'm always going to get 1.97. So 1.97 would be the better approximation for this solution. As I say, in exam, they're probably more likely just to say, use one application of Newton's method to come up with a better approximation. But of course, the square root button on our calculator is broken, and we need to work out the square root of 23. Oh no, what are we going to do? Well, basically, we can use Newton's method. All we've got to do is come up with an equation that would have the solution square root of 23. By the way, x equals the square root of 23 is not a good equation. Because remember, we just said our square root button is broken. So the equation I'm going to do is x squared equals 23. Well, we move it all onto one side, so x squared minus 23 would equal 0. The derivative is 2x. Now, I'm going to do it a little bit different in that I'm going to come up with a formula just to substitute into. And this is what you would do if you were doing it on a spreadsheet. You'd come up with the formula and then you could just plug the numbers in. And so I've come up with the formula that xn will always be xn minus 1 squared plus 23 on 2x n minus 1. Basically, I've just replaced the x's with xn minus 1. And I can just substitute into that. Now, I need a good first approximation. Yes, the calculator button has broken, but I do know that the square root of 25 is 5, and the square root of 16 is 4. The answer must be somewhere between 4 and 5. Well, 23 is closer to 25 than this 16, so I'll probably go 5. So sub 5 in, we get 5 squared plus 23 on 2 times 5, 4.8, or 4.80 to 2 decimal places. Okay, let's try again. And we want to keep going, remember, until we get the same answer. And gosh, look what's happened. I've got the same answer. So remember, we're doing it to 2 decimal places. So bingo, I've got it straight away. So 4.80 would be the square root of 23 to 2 decimal places. Some other issues that might happen with Newton's method. If you're really unlucky, you could pick a solution that just sends you into an infinite oscillation. Let me show you an example. There's our curve. I want to find that solution there. Okay, I'll make x1 there. So there's x2. All right, let's draw a 10. Oh, damn. So of course, I just got real unlucky with my first choice. And it could happen. It could happen. If you're incredibly unlucky, that's what happens. Yeah, if that happens, then yeah, you just pick a different first approximation. What would happen if I started on the wrong side of the stationary point? Okay? Yeah, so you look, say I want that one, and I decided to pick x1 over there. Now, it'll find a solution, it's just not the solution I'm looking for. Right? So some knowledge of the curve can come in handy with some of these questions. Oh, it keeps going, but look, it gets closer, but closer to the wrong one. 6E, just a handful.